Fairness and predictive multiplicity.
Hey, hi everyone. Thanks for coming back from lunch for this. And today I'm going to talk about two things. One is on limits of group fairness, and another is on predictive multiplicity. You'll learn what that is about in a bit. The work that I'm going to talk about today was done by an amazing group of collaborators and students, a very photogenic group, including Shahab and Hiwan, who presented here, Hao, Sean, Well, Lucas and Carol, and Juan Felipe, who are graduate students in my group, and Winston and Lucy, who are undergrads at Harvard College. Data-driven algorithms are increasingly used to support decision-making in applications of individual level consequence. We heard about this earlier in Sangamitra's talk. A lot of machine learning algorithms are using in applications that can really affect people's lives, things like loan approval, medicine, education, and so on. And there's been a growing call in developing these algorithms in a responsible manner. A lot of this sentiment is captured in the latest blueprint for an AI Bill of Rights put forward by the White House, by the White House Office of Science and Technology, where they suggest that one of our rights in terms of AI is protection against algorithmic discrimination. Namely, you should not face discrimination by algorithms, and systems should be used and designed in an equitable way. And this problem, this challenge of designing non-discriminatory algorithms is something that my group has been thinking about for a while, particularly from the theory perspective. And this is a really hard problem. I wanted to show this. This is a DALL-E generated picture under the prompt, a photorealistic multifaceted polyhedron against a white background. It's surprisingly good. And I wanted to show this because this problem of developing fair machine learning algorithms, protection against discrimination, is a problem that has many, many facets. There's not one definition or one aspect of fairness to rule them all. There are many different facets to this problem. And lately, we've been working on three of these facets. One is group fairness, which I'll be talking about today. Another one is predictive multiplicity that I'll talk about as well. And another one is fair use of data. This is something that I won't have time to talk about today, but you can ask me later. And recently, in the past year and a half, my group has been having a few results in exploring this area. And today I'm going to be talking about this stream of work on predictive multiplicity that dates back to ICML 2020, and also some recent results on group fairness. So to start off, I'm going to start talking a little bit about group fairness and specifically the limits of group fairness. There will be something that looks like a Converse bound towards the end of this section of the talk. So information theorists, hold on to your hats. And so just to set the stage, this is the setting that we're considering. We have a data set, and from this data set, we have a sample X. And we're going to fit this sample to a classifier, for example, a neural network, that's going to output some output H of X. This might be a score, a distribution over classes, and so on. And what we're trying to ensure here is, and what we'll be looking at this first part, is something known as group fairness. The challenge that we're trying to ensure is, that we're trying to address, is that classifier performance should not change significantly across population groups. What I mean by classifier performance, I'll be a little bit more specific about this in a few slides. What I mean by that is things like accuracy, false positive rate, and false negative rates shouldn't change across groups in the data set. So condition on these groups, the performance of the classifier shouldn't change significantly. And what I mean by population groups is exactly what is encapsulated here in the AI, blueprint for an AI Bill of Rights. These are groups that are determined by race, color, ethnicity, sex, or other attributes or intersection of these attributes. And in this case, many group fairness metrics have been proposed. The group fairness metrics are usually cast in terms of these quantities here. I'm going to introduce just a little bit more notation. So we have an input example X denoted as a random variable X, a classifier H of X that's going to produce an output Y of hat. This is also a random variable if X is a random variable. And we have these group attributes S. This is a collection of discrete attributes that we're going to use to evaluate model performance. And within this notation, there are many group fairness that we can build upon this. In the simplest case, where what you're predicting is binary, you're predicting a binary label, and your group attribute is binary as well. In that case, the way you can build group fairness metrics is the following. You can build a confusion matrix for population 0 and a confusion matrix for population 1 for these two binary populations. This is the simplest case. And by comparing entries in these two matrices, you can define different fairness metrics. So for example, if you're trying to equalize the outcomes, Sangamitra mentioned about this earlier, you're trying to ensure statistical parity. So the fractions of outputs marked as 1 is approximately the same across different groups. If you're trying to equalize false positive and true positive rates, you have a notion that's called equalized odds. But you can already see that just by comparing entries of this matrix, or for its extension for multiple classes, these confusion matrices for multiple groups, there are many, many other metrics and trade-offs that you can define on this table. And so there are many fairness interventions that have been proposed that try to ensure some notion of group fairness while preserving accuracy. And the way that these different interventions are compared and their performance is benchmarked is through graphs that look like this. You can't really see the grid lines because of the lighting. But this is a result from a now fairly old in machine learning years paper by Sir Friedler's group at Haverford College, where they compared at the time in 2019 several fairness interventions. But I wanted to show this just to illustrate how these methods are benchmarked and compared. Usually you have graphs that look like this, where on the x-axis you have something that is a fairness metric. In this case, it looks like statistical parity. On the y-axis, you have accuracy. And for different data sets, you try to see how these methods fare in terms of accuracy, fairness, performance. And as I mentioned, there's been many group fairness interventions out there. This is a recent survey that was posted a few months back on Archive by Hart et al., where they highlight over 341 publications suggesting fairness interventions, which amount to over 400 fairness interventions that exist in the literature that have been published recently. And I'm certainly responsible for a few of these publications, and we're going to talk about one more method today as well. And in general, these methods can be divided into 3 groups, right? You can think about them as pre-processing, where you change the data prior to feeding it to the model. In processing, and highlighting here a work by Ahmed, a very nice pre-processing in-processing technique that was recently published at TMLR, or post-processing methods, right? You just train your classifier as you usually would, and then you change its predictions in order to ensure some group fairness metrics. As I mentioned, I'm responsible for some of these methods as well. Just recently, we proposed a method called fair projection. I won't have time to go into details on this, but I just wanted to give you a high-level overview of how it works, where our goal was to design yet another fairness intervention, but that ensured fairness for large data sets and a multiple class prediction problems, so not only for binary classes, and could ensure fairness also for multiple groups. And there are many fairness interventions out there, but what we've found is that many of them have certain limitations. Most of them either are only benchmarked on fairly small data sets, or they only scale to small data sets. For example, they might require retraining a model multiple times, or they only consider binary classification, or only ensure fairness for binary groups. So my point, and where I'm going to next, is to show how these, try to ask and answer the question of what is the best performance that these methods can achieve. But we did propose a method called fair projection that overcomes these limitations. They can be used for any number of classes and protected groups as long as you have sufficient samples. We benchmarked it on fairly large data sets with over 1 million samples. And it can be applied to any classifier without retraining. Fair projection is a post-processing method that you can apply to basically any classifier. And again, I'm not going to go into the details, and because this is based on an optimization problem very similar to information projection that you already know from your information theory classes. You usually find this when you're studying error exponents and so on. And we spent a lot of time working on this method, and it's based on tilting a model's output in order to ensure a given group fairness metrics. You can implement it using an ADMM-based algorithm, similar in spirit to what Todd presented this morning, actually, and it runs on GPU. We have available code for that. And Wael presented it yesterday, so if you didn't stop by his poster, shame on you. You should have stopped by. It was a great poster. And you can find more details in our paper. But the point that I wanted to talk about this with you today is because of these results. So we spent a lot of time engineering this method, and we went and benchmarked it on different data sets. And again, these are the same plots that we saw earlier on, where on the x-axis, you have a notion of group fairness, mean equalized odds. And on the y-axis, you have accuracy, right? You're looking at the performance of the model average across the entire population. And these are our benchmarks. I just want to highlight this data set. If you're interested in this area or testing fairness interventions, this is a data set that we did not produce, but we translated it to English based on the university entrance exam in Brazil with over 1 million samples. That really allows you to, this is open source data made available by the Brazilian government, that really allows you to stress test a lot of these algorithms. And HSLS is another data set that Heywan mentioned on Monday, in addition to Adult and Compass, which are usual data sets in this field. And what we do here is that this star here represents our baseline classifier. So if you just train a random forest model and evaluate its accuracy and what fairness mean equalized odds it achieves, it's up here, it's very accurate, but there is quite a bit of disparity in performance. And our method here in dark red is fair projection. And you can see it's really competitive with methods that are out there. The other one that's as competitive as ours is the reductions approach, which is tailored for binary classification, but it's an in-processing method that requires retraining a model many times. So it doesn't really scale up. In large data sets like NEM, we have over 100x gain in speed because of this parallelization inherent to the ADMM algorithm. But what I want you to keep in mind here is that you can see that there seems to be diminishing returns, right? We benchmark these methods across different data sets, and they perform almost the same, right? They have very similar performance in this Pareto frontier between fairness and accuracy. And so if you benchmark this in multi-class classification tasks, surprisingly, even though there are hundreds of fairness interventions out there, at the time that we wrote this paper, we only found one that worked for multi-class classification, and was this mitigating unwanted biases with adversarial learning by Zhang et al. And our method also performs very competitively. Yeah.
That's not quite correct.
Okay, so you can challenge me afterwards. And if you know a method for that ensures good fairness for multi-class classification.
This is not post-processing. This is in processing.
Oh no, I'm not claiming it's post-processing. I'm just claiming that it works with multiple classes. All right. So, but the question that I want to arrive is what is the best fairness accuracy frontier, right? Because if you look at these plots, there seems to be a diminishing returns phenomena here, right? We're over-engineering these methods. And it would be nice to have something that looks like a converse result, stating that for a given data set, obviously under certain assumptions on the data distribution and so on, can we argue that there is a non-achievable region? Can we design a converse result and show that we're really close to that? And I guess this has been a trend in a lot of the talks today, but since I'm at Berkeley, shout out to David Blackwell, because we're going to use exactly his data processing result on comparison of experiments in order to delineate something that looks like a converse result that allows us to compare these methods against what would be the ideal information theoretic best. So that's what I'm going to do next. Is it clear? I'm going to be talking about what is this converse result here. So let's return to the setting that we had earlier. So just to refresh your memory on notation, so we have these group attributes S that denotes membership on a given group. We have this label Y, that's a true outcome that we use to train the model, but in practice, it's not observed when you deploy it. Your input example X and your classifier H of X, for example, a neural network or something of the sort. And this forms a Markov chain like this, right? From S and Y, you feed it to X. X may include S. You may use this as an input to your classifier, and your classifier is going to generate an output Y of hat. There's this Markov relationship here. And we're going to assume that the joint distribution between S, Y, and X is fixed. We usually don't know this distribution, but for the purpose of designing a converse result, we're going to assume that it's fixed. Now, ideally, if we could do something like this, if we could characterize the set of all distributions, and if we knew the distribution between S, Y, and X, and we could characterize the set of all mappings from X to Y hat, we could potentially characterize this, well, actually, in this case, we would characterize exactly what is the optimal parental frontier between accuracy and fairness. We could try to solve this optimization problem where we find the best distribution between Y hat and S and Y, given the constraints posed by this Markov relationship, in order to maximize accuracy and controlling a given fairness metric. And so this is what we're going to do next. Our goal is to find simple ways of characterizing this set of distributions so we can plug this into this optimization problem and plot something that looks like the optimal Pareto frontier where we can benchmark existing methods against it. So I'm going to show how we did this through a cartoon. So you can think about the set of all mappings from SY to Y hat as this blue set here. So this is the set of all conditional distributions. In the case that SY and Y hat are binary, this is the set of 4x2 matrices that are row stochastic matrices. And if you choose one machine learning model that you deploy in practice, you're inducing one point in this space, right? Because that will induce one mapping from S and Y to Y hat, for which you can then evaluate fairness and accuracy and so on. Of course, you have constraints to the problem posed by the data generating process, and that restricts the set of achievable conditional distributions given these constraints here, denoted here by this orange set here. And as I mentioned before, our goal is that it should characterize the best fairness accuracy frontier, and most fairness and accuracy metrics can be cast in terms of this joint distribution. Remember the table that I drew earlier where we had confusion matrix for group 0 and confusion matrix for group 1? That's exactly casting a fairness metric in terms of properties of this joint distribution here. So if we could characterize if we could characterize this, we could characterize the set that gives the best information-theoretic frontier, which is exactly this set here. So the challenges in doing this is first, obviously the data distributions are unknown. So we don't know that in practice, we only access that from their samples. But even then we could relax that to create what I'm going to show next, synthetic experiments to benchmark existing methods. But the other challenge is that these input features X might be actually quite high dimensional. And these constraints, for example, equalizing true positive rates and false positive rates, they're non-convex integer constraints that are very hard to deal with. So in order to address this second point, the key idea that we have is instead of trying to characterize this set exactly, we're going to create a bound on this set that's more computationally tractable, right? A simpler bound. Because then if we solve this, this optimization problem over this outer set here, what we get is an upper bound. We're solving the optimization over a larger set, so we get an upper bound for the best fairness accuracy frontier. And just as a warm-up of how you could do something like that is that you could constrain the set of distributions using something like the data processing inequality, right? So if you give me the mutual information between sy and y hat, we know that that mutual information cannot be greater than the mutual information between sy and x. And imposing this one constraint on this set already restricts the set of all possible distributions that you can achieve. The challenge here is that this bound might be very, very loose, right? It's not even clear if mutual information is the right metric. So, and this is where Blackwell comes in. And we use Blackwell's result of comparison of experiments because this result gives you a precise characterization of data processing, right? That we have this, that this Markov condition holds only if P of X given Sy is more informative than P of Y hat given Sy. And you can write this very precisely in terms of this theorem here. So this is Blackwell's theorem that given A taking values in N for any true distributions P of X given A and P of Z given A, you can create these things that look like these likelihood vectors. And you say that P of X given A is more informative than Q of Z given A if for any convex function phi, this expectation on P is greater or equal than the expectation of the same function measured according to Q. And you can already squint at this and see that if I pick this convex function to be something that looks like V log V, also a convex function, you recover something that resembles the data processing inequality from mutual information. But we can choose any convex function here. And the one that we choose are piecewise linear functions to try to approximate the set of achievable joint distributions. And in fact, Blackwell shows that in general, this is sufficient. So this problem of choosing convex functions that we're going to use to bound the set of achievable distributions, this can be formulated as an optimization problem, a problem that's the difference of convex optimization functions, the difference of convex functions, and we can optimize for that and find successive cuts, these linear functions to approximate this set. And once we have this approximation, we can solve this optimization or try to approximate this, this optimization over this restricted set, and that will give us an outer bound. Yes?
Are they tangents or they're not tangents?
They're not necessarily tangent because we're not solving it exactly. I'm not going into the details here, but like we're solving it using, yeah. So they won't necessarily be tangent. Yeah. But you're always on the outside. You're always on the outside because you impose this as a constraint to the optimization that you satisfy. It's about here. So you're always on the outside, but you're not necessarily touching that set.
So how you do it? Like what kind of warranties you have for the link? Are you running an ellipsoid?
No, we formulated it as a difference of convex functions, and we successively keep like finding these cuts. So let me show you the results of how this works. So what I'm going to show next are semi-synthetic experiments where we assume that the data set is the ground truth. So what we do is that we get one of these usual data sets and we sample from it with replacement and use that to train and test our fairness interventions. And it's kind of an approximation because it shows that, because we assume that the actual data set is the ground truth. And then we apply this method to create this outer bound and compare it to the fairness interventions against that. And this is where we're at. So these are results for the adult data set. And the red line here is the fair frontier that we call it. It's the result of this optimization problem. And we repeat this for Compass and for German credit. And as you can see, the reductions approach and fair projection are right on the money. Like we're really, really close to the optimal frontier. So this doesn't mean that if you try this with different data sets and so on, it wouldn't be close. But it means that for these data sets that are widely used in the literature, there seems to be diminishing returns and continuing to propose the next 100 fairness interventions that optimize solely for fairness and accuracy. So the takeaway here is that it seems like we're close to the information-theoretic optimal fairness accuracy frontier, at least in these somewhat synthetic experiments that we've done before. Do
you know how to compute this shiny data set?
Well, in theory, you can do it. Like there's some issues with the optimization problem that we can discuss offline. Yeah.
Should I view this as a limitation of the data set then? Like we have not collected the right data.
I actually interpret it differently. What I find out, we have a discussion on that in the paper, like because there's but the way I interpret this is that the optimization, the fairness interventions that we have out there, they're already really good at achieving this fairness accuracy frontier, approximating it. Like this remaining kind of curve that we have, we call that aleatoric discrimination, which might be biases that are inherent in the data, right? And that might be due to the data collection process and so on. But removing those biases, the epistemic limit that comes from your choice of model, your choice of fairness intervention, it seems like that gap is really close to zero. So, so that motivates us to look at other aspects of fairness as well. Like, so because there seems to be diminishing returns and continuing optimizing for fairness and accuracy. And now I want to talk about another problem that we've been looking at called predictive multiplicity. So in order to introduce predictive multiplicity, I need to talk about the Rashomon effect, and which I'm going to talk about next. So consider again the problem of fitting a machine learning model where I have a set of samples, say X-ray images, and I'm going to fit a neural network in order to predict some label from this image. This model is parameterized by some parameter theta. And let's say you're predicting if this this chest X-ray has pneumonia or not. During training time, you have to make a ton of decisions prior to training in order to initialize this process, right? You're going to set the random seed to initialize how you're going to initialize your weights. You're going to set dropout rates, shuffle your batches, and all that stuff. Let's call that different random initializations. And as you vary these arbitrary choices, these random initializations, you might, after training, you might end up with a different model. And these models, when you evaluate them, many of them might achieve very similar performance. Basically, their empirical loss might be below a given threshold, the loss that they achieve. This phenomena, where you have multiple distinct models with comparable performance for a given learning task, is known as the Rashomon effect. It was, as far as I know, first identified by Leo Breiman nearby. He was at Stanford. And the name Rashomon comes from a Akira Kurosawa 1950s movie, Rashomon, where different people report the same crime from different perspectives and give different explanations of what happens. And this parameter epsilon here is what we call the Rashomon parameter. It determines like the size of the set of competing models. And we have a result that we're going to be talking about at ICIT this year, where this epsilon, you can already see this, that it will always be non-zero if you're evaluating your model on a finite data set. So there's always an inherent uncertainty, a confidence interval up to which you can know the performance of your model. And within that uncertainty, that confidence interval, you might have, just by perturbing the weights of your model, you might generate many different competing models. So you can think about this Rashomon effect as almost creating these islands in your model space, especially if your model is your hypothesis space, if this space is non-convex, where you have multiple competing good models, models that satisfy their average performance is below a given threshold. So that's a Rashomon effect. So where predictive multiplicity comes in is when you look at the predictions of these models for one individual sample. So you have these multiple competing models that based on accuracy alone, you can't distinguish them. But when you feed one sample to these models, they might produce conflicting predictions. So in this example, for different, for example, for this X-ray image, different models might give different incidence of pneumonia rate. And that's what we called predictive multiplicity in a paper in ICML 2020. And as far as we can tell, predictive multiplicity occurs in many learning tasks. So we've found it in image classification problems, or you can find samples that have these conflict across competing classifiers, in text classification, in audio classification, and so on. And predictive, yeah.
Sorry, what is the difference between the competing classifiers and other trained or other instantiators?
Here, in these examples, the classifiers were generated via retraining. These are neural networks, and we just retrained them with different random initializations, same data set, and ended up with different models, but with different random initializations.
Sorry, so you were saying that the expected loss is different from the individual?
No, the expected loss is similar, average over
Yeah,
a
sorry,
data set,
I feel like
but certain individual predictions may conflict. For example,
meaning that they're different.
they're different.
And why this is surprising?
Well, I'm not saying it's surprising, but
It should be actually.
yeah, well, they don't agree. But I can tell you why this is important. The reason why this is important is because if predictive multiplicity is not accounted for, in practice, decisions supported by machine learning models may depend on arbitrary and unjustified choices made during training. So someone might be using the model and think that this prediction is due to the features that I'm using as an input to the model, but they're actually due to some choice of random seed made prior to model development. And this is this is an argument made by Creel and Hellman in a paper in the Virginia Law Review that particularly in sectors dominated by few algorithms, like this has a risk of creating these algorithmic leviathans. And these are because of these arbitrary choices, and if these algorithms control access to critical opportunities, you might be excluding certain individuals from these opportunities. Let me give you one example. One is from the Brazilian government, who actually announced a year ago that they're going to use AI to grade the handwritten essay component of the university entrance exam in Brazil. This is an exam that I took, the ENEM exam, and they're going to be using machine learning models to give grades to essays. And of course, for some students, you don't want the grade for that essay to depend on some random seed. You should initialize your convolutional neural network. The folks who are developing this, by the way, are at the Graduate School of Education at Harvard, like some of the researchers doing this. Another example is FICO scores and credit scoring, right? These are algorithms that control access to critical opportunities, loans, right? And if you want to get a loan, your data will inevitably be fed to one of three algorithms. So we explored this problem, different aspects of this problem. I'm going to talk about one result that we had recently on how can we measure and report predictive multiplicity. This is based on a NeurIPS paper from last year. And I'll just give you a high-level overview of this. Because one issue that we face is how do you even report this conflict of scores that exists among multiple models, given that you have some approximation of this Rashomon set. So given an individual sample, and when you feed it to competing models with similar performance, particularly in multi-class classification problems, you will get conflicting predictions. You can think about this as the output of a model over three classes, where you say with probability with 0.05 your class 1, 90% your class 2, and 5% your class 3. So if you collect these conflicting predictions, these conflicting scores, you can collect them in a set that will depend on your sample and on your Rashomon parameter epsilon, and create this set of conflicting predictions. And the question that we ask is, how should we measure this score variation, right? How should we report this to a user and eventually build on this to measure this multiplicity phenomena in practice? So our goal was to create a function that would map this set into a number that would capture this variation, this disagreement in score. And we wanted this function to, we postulate that this function should have certain desirable properties. We call this a multiplicity metric. And it should be between 1 and C. So where 1 means that there's no multiplicity, and C is the number of score of classes that you're predicting. So 1 means that all of these predictions agree. And you want this value to be 1 if and only if all of the predictions are the same. You want it to be C, the number of classes that you're predicting, only if every single class can be perfectly predicted by some classifier in this Rashomon set. And you want this set to be monotonic in the sense that if you add more scores to this set, your multiplicity metric will not decrease. So we did this using actually tools from information theory. We call this we proposed one metric called Rashomon capacity. And the key idea here is that given a set of competing predictions for a given sample, we view each prediction as the role of a noisy channel, right? So each prediction is a probability distribution over classes. You can view this as a role of a noisy channel, and then you compute the capacity of this channel. And you can compute it in this way, right? So this is not your usual way of seeing channel capacity. This is a more variational form. Usually you're accustomed to see maximize mutual information over input distributions, but this is essentially the same thing, where you're finding a centroid in terms of KL divergence of these competing scores and maximizing over distributions over models. And note that this is a metric that depends on for each individual sample that depends on this Rashomon parameter here. And the multiplicity metric that we propose is called Rashomon capacity. It's just true to the capacity. And it's not difficult to see this could be an exercise in an information theory class to show that it satisfies all these desirable properties. So Rashomon capacity satisfies these properties, and you can compute it in practice using the Blahood-Arimoto algorithm. So in the few minutes that I have left, I want to talk a little bit also about another recent paper. And I actually think this is really important on predictive multiplicity and differential privacy. And this is a paper that we're going to be presenting at FACT in a few weeks. So consider again the setting that we had, where we're predicting, given a set of samples, we're predicting, say, presence of pneumonia in these X-ray images, but assume that now our data is private, right? This is privacy-sensitive data. So one way of ensuring privacy here, and we already heard a lot about this in this workshop, is that we can ensure DP using randomization during training, right? So we can, for example, do output perturbation. What that means is that you can perturb the model weights after training, or you can use objective perturbation. Again, this is based on Anand's work, where you add some random perturbation to the objective, or you can do things like DP, SGD. But I'm just going to collect all these different strategies as using randomness during training. And if you choose a given random seed to initialize your random numbers generator, after training, you're going to arrive at a given model, right? A given set of weights. And with different initializations, you're going to have different runs of your differentially private algorithm, and that's going to lead to different models at the end. And even though these competing models, they offer the same level of privacy, they can make conflicting predictions to individual samples. And this conflict in predictions, this inconsistency in predictions, is not equally distributed across all samples. So some samples suffer more. It does not affect all samples equally. And this is something that's widely underreported, because you might use a differentially private model and you think that, well, this prediction is due to my features, but it might actually be an arbitrary artifact of noise used during training in order to ensure privacy. And just to give you a flavor of how this shows, this is an example on synthetic data, where we train a logistic regression classifier using objective perturbation, where we add random noise to the objective in order to ensure DP. In this case, we train 5,000 models on simple two-dimensional mixture of Gaussians. And we only keep models that have 80% accuracy of a baseline. Of course, you wouldn't do this in practice because that would violate differential privacy, but this is what we're doing here. And what we report is disagreement that over these 5,000 runs, what's the probability that a given score would change for a given sample? And what you observe is something like this. So as epsilon increases, this is not the same epsilon as the Rashomon set. This is epsilon and epsilon DP. So higher epsilon is lower privacy and smaller epsilon is higher privacy. That the amount of disagreement, the probability that a score would change, does not impact all the samples equally, even though your baseline classifier, the optimal one, is this 45-degree line here. You would always get the same classifier if you train without noise. And we have many examples on this on our paper. I think the final version actually was just posted on the FACT website. And you can see again that this effect of predictive multiplicity does not affect each sample equally. It's not equally distributed across samples. And it's not equally distributed across groups in the data. You can see variation of the incidence of this multiplicity phenomena against groups determined by age, for example. So I'll wrap up here. The takeaways is that always measure and report predictive multiplicity. I think in applications of individual level consequence, this is as important as reporting test error. Multiplicity is a hidden cost of differential privacy, as far as we can say, and the folks that reviewed our paper for FACT said as well, that this had not been identified before. Decisions supported by machine learning models without regard to multiplicity may seem arbitrary, right? And there's still a ton of open problems here. We don't know how to efficiently characterize this Rashomon set, nor report multiplicity in a differentially private ensuring way. We're still exploring how to do that. So I'll wrap up here, thank my sponsors, and I'll be happy to answer any questions. Thanks.
So DP could be looked at as another hyperparameter in this whole space. How do you really tease out maybe in a logistic model, it was easy to do, but how do you tease out the effect of the other hyperparameters in DP?
I think in the synthetic example that I showed, we only had, like, if you train without privacy, you only have one optimal model. So in this case, this randomness comes entirely because of the added randomness when training.
The capacity that you defined is x dependent on each x, right? So I don't remember if you had a plot of like what does that look like over the training set or something?
I removed that plot because of time, but we can discuss it. But what I can say is that it depends on the accuracy of your model. But in many classifications, especially in many data sets, especially image data sets that we train with like neural networks with many local minima, there tends to be a tail of samples with high rational capacity. So there tends to be like something like 10% in Cypher 10 or 15% of samples that, yeah, and these are not necessarily points that are near a decision boundary. These could be points that are simply outliers from the data set as well. Yeah.
Quite curious about how much agreement there is, not across models, not across retrainings, but across over time. So I saw this work that showed that if you track a model over time, it's
Like during training?
yeah, during training, and you ask its prediction on individual points, the points that it like oscillates on are more likely it's a good predictor on mislabeling. And this seems very related to the DP point of like basically if they're mislabeled, it seems more likely that they're being relevant, and this seems really related. So anyway,
we haven't thought about that at all. That's a really interesting thing to explore. Yeah, like in training multiplicity almost.
yeah, exactly.
Do you think there's a way to think about this notion, not just for many different fitted models, but just for a single model in terms of like a sensitivity analysis, like how sensitive the model is, and you can somehow differentiate that point where you fit it, like see how much things change.
Yeah, that's such a good question. I was actually discussing this with Sangamitra earlier because that is related to the idea that she presented of counterfactuals, right? Where given that you might have an inherent uncertainty, a confidence interval in evaluating your model because you simply have finite test data. Like if you just perturb the weights of your model around that point, like which points are the most sensitive? Like that's something we're exploring.
Okay.